store information. So now in part 2, we're going to look at the building blocks for dealing with information that's stored across multiple machines, so multiple servers. And there's some obvious reasons why you would do this, right? One is scalability. You can obviously get much larger across multiple machines. It provides fault tolerance. So if you have things spread across multiple machines, then if one of them goes down, then requests can go to a different machine. And then it also can even improve your latency, especially if you consider, people around the globe. And so you can have an Australia data center, an East Coast US data center, a West Coast US data center, US, whatever. And so if requests are going to a nearby data center, that's certainly going to be a lot faster than if you're sending your request all the way, say, across the Pacific Ocean to a data center in Australia, something like that. So the author mentions that there are these different architectures. You can have shared memory, shared disk architectures. People worked on those for a number of years and could do types of vertical scaling, but ultimately, you're going to have limitations on scalability. And so, so the shared nothing architecture is where basically you have independent machines. They communicate over the network, but they have nothing in common. And so if you go to the extreme of having multiple data centers, then you basically cannot do shared memory or shared disk. And so ultimately, that's an easy example where if you have a data center in Australia, a data center in San Francisco, then you have to go to a shared nothing architecture. So we're going to start talking about those types of issues. And so the first one is replication. So how do you have multiple copies of your data in multiple places on multiple machines? And so the problem with replication is if you had something static, so if you just had some like dictionary that you wanted people to be able to access, then you can just make as many copies of it as you want and life is fine. The problem is any system that allows changes where you have generically writes, okay, it could be inserts, updates, deletes, whatever, but any form of a write, now basically that change has to be reproduced on every single copy that you have, every replica that you have. And so this chapter then talks about the different strategies people have come up with dealing with that problem. And what we will see is that when you have systems that are changing, when you have writes, that no matter how you implement things, stale reads are possible. And there's different phenomena that to the user will look wrong. And then as we get into the more complex topologies, then not only can you have stale reads, but you can even have writes that at the time that the user performs the write, they get back an acknowledgement that says the write was successful, yet their data will be lost. It'll be overwritten. So those are the issues ultimately that we're going to talk about here in replication. So before I jump in and just kind of go through the chapter, I just wanted to see if anybody had any particular questions, things that we want to make sure we hit on. Not necessarily expecting that you will, but if anybody does, then happy to note it here just to make sure that we touch on those things.
I had a generic question, and that is, I found this information really fascinating, but I've never really put it in any kind of practical application. And so it's a question for the group. Has anyone really used any of the information in here, like chosen a different database or specifically chosen a specific replication schema because of the information in here? As a general rule, I mean, in my experience, you buy Oracle or you buy SQL, and then you kind of set it up in a pretty stock standard way, the way that probably 95% of everybody else has set it up.
Well, Stephen, I had significant experience with this. When I worked for British Telecom, we were designing the global IP network. And one of the problems you get into with networking is what time is it?
Sure.
Because you have the whole world, and then how to synchronize like routing updates. So like for large autonomous systems, we were using BGP, but it would only update you only get route updates every 30 seconds. And so new protocols had to be written to allow fast convergence of networks. So that was just an example that I'd worked with.
Oh, okay, cool.
Yeah, I can say none of my companies have been large enough to need this kind of replication. Obviously, if you imagine a big company like, you know, Facebook, Twitter, Amazon, right? You've got customers around the world. And I think the one takeaway I would say is, right, so you may not be the person who has to like build these systems. You don't have to implement them. But what you want to know is that you can have stale reads, and if it's a multi-leader or leaderless application, then you can have lost writes. No matter what your system is, no matter how you configure it, it is impossible to configure it to make that impossible. So now you do want to pay attention to not only the product you choose, but also, you know, how you configure it, because you can't. So for other things, you can just sort of say like, well, it should just work, right? It should just be transparent to me, and I don't need to know the gory details. But in this case, because there is no, you know, magic pill, silver bullet, you know, you kind of do need to beware of that someone's making these decisions, and that they are going to at some point have implications for you.
Okay, fair enough.
I have some experience working with the Google Spanner database. I'm not saying I develop it, I just use it. So as a user of that database, it happens like you can choose, if we want to read some data from Spanner, you can choose a strong read, which uses a strong consistency model, or you can choose stale read. So you can say, oh, it's fine, I just read the data within 30 seconds. It's good enough for me. So in terms of your use case, if you are not that care about strong read with the latest data, you choose like, it's okay to read all data within 30 seconds, then you can get a significant performance improve, something like that.
And I'll say that a lot of that stuff is kind of based on, you know, your application, and then within organizations, applications tend to flock together. It's just a, you know, one of the emergent behaviors, right? So like for us, we have a bunch of commerce applications that tend to be system of record kind of stuff. They follow much more single leader kind of models. And then we have other applications on our social side where we're not, we play it a lot faster and looser. And so it's like, yeah, you know, we'll do inconsistent writes on a multi-leader kind of setup and just be like, yeah, that's fine. You know, it'll reconcile or not. Yeah, it's not a huge deal. So it very much comes down to, we look at the application needs, or, you know, how lax we can be with it, and then trade that off. It always tends to be a trade-off for latency. So.
Okay, cool. So there are some people who have actually had to think about this stuff. Okay. Because I'm like you, Chris. I mean, when I've implemented stuff, even at the national scale, we've tended to just buy very standard products, like I said, Oracle, SQL Server, that sort of stuff. And then you typically implement a sort of a single leader kind of model.
Yeah, and I will say a lot of this, like, we have stuff, you know, we have a bunch of stuff in Cassandra databases, we have some stuff in Dynamo, you know, databases with different, you know, even stuff in, say, S3 for some of our big data. And I mean, S3 changed some stuff recently, but they all have different consistency properties. And it's not that we're actually implementing any of these features. We look at the technology and we say, oh, okay, this is what this technology is better at, or how we can use it well. More so than saying, oh yeah, we're going to go in, we're going to implement our own multi-leader algorithm. Yeah, we don't do that. We still use it as some kind of, you know, either open source or packaged product.
Cool. Thanks, guys. Anybody else have questions, things they want to bring up front?
I think for me, this was an interesting chapter because I've worked on some small projects, and I've never gotten to the point where I've needed to actually horizontally scale something. And so it was kind of just interesting to go through the thought experiment of how exactly do people typically do that sort of horizontal scale, because in the past I've not really looked in that direction.
Yeah, I mean, I like these as thought experiments. I think maybe it's because I'm, I don't know, like sort of, I don't know how you describe it, but like for me, like if you say, I'm going to set up a system this way, like figuring out the ways in which it could fail, it could behave not the way you expect. Like I find that to be a pretty interesting kind of a question, you know. I've always felt like I was a pretty good software tester because it was easy for me, rather than like trying to do use cases where things would work, very easy for me to like get in the antagonistic role of like, what if I do this weird thing that you weren't expecting, you know? It's like, oh, you wanted a number? Well, I won't just try letters, I'll try control characters. I'll try doing all sorts of weird things to you. Okay, cool. So we're going to talk about 3 different styles. We're going to start with single leader replication. This is the simpler form. And, you know, you can imagine in theory, it's relatively straightforward if you just have one leader and one leader only. And all the writes go through that leader. They're always sequential. And then the leader just says to however many followers you have, hey, I got it right, and it's sending those out always in the exact same order that it received them. So sort of this worldview is in the same order, you know, everywhere. There's some complexity, you know, so you can have synchronous forwarding of writes from the leader to a follower, and that's going to introduce latency. So the risk is if you don't make sure that at least one follower has a copy of that write, then of course if you have a failure somewhere on your leader, then you could lose that information. So the client could see a success on the write, but you could ultimately lose that information. Asynchronous, much lower latency. You just simply say, fine, I've got the write, I'm going to forward it on at some point. If they're all 100% asynchronous, then we have the situation we ran into. So maybe you could do something like, you could say, well, I'm going to do one synchronous forward. Theoretically, you can purposefully have your synchronous, you know, follower be close to your leader. And so then the idea is that ideally all of those are happening really fast, you're introducing very little latency. And then whatever other replicas you have, those followers, you can do those asynchronously. They can be a little bit slower, but that still gives you a lot of protection against failure or whatever, because you've got multiple copies. And it also allows you to scale up your reads, because the reads can come from any follower. It doesn't have to come from the leader. So this seems like, on the surface, to me at least, it seems like, okay, this is a pretty simple architecture. You know, what could go wrong with something like that, right? And so in this architecture, if a follower fails, it's pretty straightforward. When it comes back up, then it needs to just basically catch up on everything that it missed. So if it missed a little bit, then you're just gonna, you know, have the leader forward whatever writes it missed, just like the normal fashion that it's always forwarding writes. In theory, if you really, you know, if you were down for a month, then you're probably not going to do it that way. So then you're going to do some kind of snapshot backup, apply that to the follower, and then just have incremental writes since the snapshot. Where things get interesting is if the leader fails. Okay, you obviously don't want this to happen, but worst case scenario, you know, this can happen. And so the author doesn't really explain like all the things. Some of these issues are going to come up later in other chapters, but he just basically, you know, lays out a bunch of issues. So if your leader fails, what you're going to do is you're going to promote one of the followers to become the new leader. Okay. Issue number 1, well, how do you know the leader's failed? If you set a really long timeout to be really sure that the leader's dead and gone, then that means that your application might be down for that whole time while you're waiting for that timeout. If you set it too short, then it might just be a simple delay and the leader's actually perfectly fine. and there's no need for you to actually fail over. All right, so now let's just say we do think we have a failure. How do you choose the new leader? If you have 5 followers, which one of the 5 should become the new leader? Is there a way we can tell which of them is the most up to date? Is one of them, more up to date than the other? And then once we hypothetically decide, okay, node C is going to become the new leader, how do you make sure that everyone agrees and everybody knows node C is the new leader? And then worse yet, when the old leader comes back, is it going to think it's still the leader? How is it going to know that now node C is supposed to be the leader and I'm supposed to be a follower? You have 2 leaders. When clients are accessing the system, how does the client know which node is the leader? How do I know to send my writes to node C instead of the old leader? So these are all these issues that can pop up just from this one activity of figuring how to do promotion and how to notify everyone, both followers and clients, that you have a new leader. So so these are sort of sneak previews to chapter 8 and 9. So we'll get into more issues about like how to do consensus and things like that. And I thought it was an interesting comment. I've never managed one of these, but because this can get really thorny, there are, a fair number of organizations where they do not try to do automatic failover. They have an operations team that's 24/7, and when it looks like the leader might not be responding, they set off an alarm. And ultimately, it takes a human being to say, I'm going to apply this change. I'm going to say, leader is down. Okay, node C, you're the new leader. Tell everybody node C is the leader. And then you don't have this consensus and back and forth, kind of an issue. It's just a human being decides, picks, and then ultimately issues an architecture change. All right, any questions about that before we talk about how to actually implement the forwarding of the rights?
Okay, maybe it is a bit, ahead of the time, but about choosing a leader, as far as I know, all information is copied the same as any other information from leader to a couple of more nodes. And this is how they use. Pretty much it is a, choice between these 2 nodes, which I guess is not so difficult.
Yeah,
are you going to talk about it now? And I shouldn't have said, ahead.
Yeah, I have not read chapters 8 and 9 yet. I skimmed ahead a little bit, but I haven't really read. But you can imagine that you could have a situation where, let's say you have a leader and you have 8 followers. Well, maybe one of those 8 followers recently failed, and so they're busy catching up. So they would be a bad choice to be the leader, right? Maybe one of the 8, another one of them is in Australia, and so things are really slow, and so they didn't actually get all the most recent rights from the leader yet. So there's little things like that. I don't know. Maybe we'll see more stuff.
Okay, it is not from this book. I read another book which was called NoSQL from Mere Mortals. I thought, well, I'm mortal. Fits for me. Anyway, this is how they explain it over there. But maybe we'll see here something different.
Mm-hmm. Okay, cool. Thanks, Maya.
Okay, sorry, real quick question too. Has anyone worked on or at an organization where they have a team on call to handle this transfer? I'm just, because my background is I used to work with this type of replication databases, but it's mostly like, let SQL Server handle it, or, let the Exchange databases handle it, not a team that does any of this. So I'm kind of curious on people's experiences with that, if there are anyone.
I mean, everything depends on the technology. A lot of the recent stuff definitely is able to do automatic failovers. And they have, robust systems in there, but those can always go sideways. So it's something to keep in mind. But yeah, I'm on the team that gets these calls.
So in your situation it is, like you said, when the failover faults for some reason. That's when actually you're called, as opposed to the lead, something's happened to lead and now we have to choose another one.
Yeah. Yeah. I mean, a lot of these things, they're N+1 systems. So usually like we'll deploy, say 3 of them. And that way one can fail and we'll still be able to work within a quorum system, or we'll still be able to work within, you know, it's like, oh yeah, okay. As long as 2 don't fail, right? You know, so we get that little extra resiliency, sorry, robustness.
Okay, cool. Yeah, I mean, that makes more sense to me than what I guess I thought. But yeah, I was just curious. But thanks, Chris.
Okay, so the next section is, we just talked, I waved my hands and I said, hey, whenever the leader gets a change, it just sends it off to all the followers. So there's a couple different techniques where how you would actually send that information. So without going into the gory details, we can talk about, you know, sort of 4 different ways that you can forward this information. So the first is statement-based replication. So basically, if somebody says, update, you know, this information, set a certain column, field, whatever, new value equals 5, then you just take that exact same statement as it came to you and you say, hey, here's the statement that I just ran. Go ahead and run the same thing on your copy. And so where this runs into issues is where you have sort of non-deterministic behavior. So if, for example, that query had a random number generator call in it, then you're not necessarily going to get the same random number on every replica when you run this. And there's other things that are non-deterministic, like current time is not going to give you the exact same value on replicas. And there's other weird kind of side effects you can have, like if you have an auto-incrementing primary key kind of a column, that sort of a thing. So there's theoretically workarounds you can do where you have a list of deterministic and a list of non-deterministic commands, and then you have to do something special if you see non-deterministic. So if you want to avoid that altogether, then instead of sending the user's statement, you can just simply say, okay, I've got my database, however stuff is encoded, it's on disk. Basically, I'm just going to say, okay, go to this block, write these values over, you know, go over here, write these values, blah, blah, blah. And so the risk for this is, one, it can be very voluminous if you have a large update to just say block by block by block, here's all the updates you need to make. But then the other issue that the author brought up is, you know, so I have thought about a lot of these other issues, but this evolvability, maintainability thing is something that I mostly hadn't thought about till I started reading this book. So if you want to be able to do, you know, whatever warm upgrades, and so now you're going to upgrade one of the followers to a new version, well, if that changes the physical layout of any of your structures, now you're in big trouble if you're using this physical write-ahead log shipping. So then there's this sort of intermediate level where you can say, okay, instead of going all the way to the low level and shipping you this detailed physical updates, I'm going to send you logical updates. I'm going to say, here's a key and here are values and here's what I want you to do. I want you to insert, delete, update, whatever. And then finally, the fourth option is you can just simply say, okay, user, you go and write your own code. You write your own triggers and basically say what it is that we do. So in this case, then you can be as low or high level as you want. But of course, if it's user written code, then you run the risk that maybe there's some edge case that you didn't think of. Maybe you have bugs in your trigger code. I have not written replication triggers, but I have written database triggers, and I can certainly say it is easy to have bugs in your trigger code once it gets beyond the very simplest of triggers. Okay, so now what I thought was kind of the fun, interesting stuff, right, is how can this stuff break? And so so the author gives examples of a different way. It's all ultimately replication lag. If you have really slow connections or slow servers or servers that are really just backed up right? Like they're getting the information from the leader in a timely fashion, but hey, I've got this backlog of 50,000 other writes that I got to process first, because I have to process them in sequential order. So even though I may have received that update from you, it doesn't mean that I'm caught up. Maybe I'm running slow. So so it talks about a few different ones. I just wanted to pause here and just see, does everybody understand? So I pasted one of the diagrams from the book in here. I didn't want to paste them all. There's lots of really great examples, but I just included this first one just to make sure if people had any questions about these diagrams, because this form of diagram is used like a gazillion times in the book from here on out. And so we have time, which is represented sort of on the x-axis, and time moves forward from left to right. And then vertically, we have different computers. The computers could be servers, like leaders and followers, or they could be clients. So just like you as an end user running an application, making a request or whatever. And so if you go horizontally, each swim lane corresponds to one computer. And so then the communication between computers is these arrows we see. And so when they're really fast, then the arrows are very close to vertical. And when the communication's super slow, then that's when you see a very flat horizontal kind of a line. So everybody cool with these diagrams?
I have a
All right.
question,
Yeah.
real quick. So I haven't come to a point where I had to facilitate what we've been talking so far. So I would imagine with leaders and then followers working with multiple servers, you would have to have some like coordination, like how like Zookeeper is one tool that manages that for I think for Kafka. So from people's experiences, are these typically like built in with the specific like DB that they're using, or are they using something on top of that to coordinate all this?
Fair question. Anybody able to help answer that?
I was going to say, outside of Zookeeper, I'm used to them being built-in mechanisms, and that to be the predominant one or predominant way. So Zookeeper tends to be a nice coordination aspect that some software out there has decided to incorporate, but I still feel like it's in the minority, though it's definitely the plurality, if that makes sense.
So with these type of options or solutions, or that I guess we'll be looking at sometime soon, it's a matter of like accounting for these possible cases and then configuring our databases to handle these. Is that, I suppose that's the case?
For most, I would say for most software I've seen, yeah.
Yeah, so like for Cassandra or something like that, if you have node failures, that's primarily handled by Cassandra itself.
Yeah.
Right.
So a few years back, I had looked at Oracle's product Golden Gate for a company. And what was kind of interesting to me, I mean, so it's basically the same thing. It's just a synchronization layer or a coordination layer you put on top of relational databases, specifically aimed at Oracle. But one of their claims, which again, I never got to the point of being able to test it, was that they could actually synchronize any relational database. So you could have an Oracle database at one location and then a SQL Server at another location. And because this was a layer on top, it would actually synchronize them and coordinate them.
Yeah, Golden Gate is a statement-based replicator, if I recall correctly. So that's how it tries to go anything that's SQL, ANSI, 1995 compatible. It would be able to do that replication on.
Mm-hmm.
It is one of those that's kind of, it definitely makes the leader follower model, but I think to the point of like automatic failovers and everything like that, it's one that still expects you to be managing a lot of your failover characteristics. or sorry, a lot of your failover events.
Yeah, I can say I haven't done it recently. Like SQL Server, Microsoft SQL Server, I've set up replication, and there was no automatic failover. You know, the replication lag and catch up and all that, you know, was handled automatically. But your single leader goes down, you got to deal with
Isn't
I've worked with Oracle, and I've worked with MongoDB, and MongoDB definitely has that, where it will do the election and then vote for a new leader, and you have to set up another node that manages all of that. And then I think, if I remember correctly, Oracle also had that built in, where you could have it so that it would automatically fail over to another instance, and then that became they used to call it master slave. That became the new master.
Yeah, the thing that I find a little bit scary is that if you have a failure on your leader, there may be rights that the leader told clients were successful that have not yet been replicated to the followers. And so you can have a loss of data. And I think that's why, you know, back in the day, I mean, I have not done this recently. I'm sure that these products have evolved and gotten better. But so if you do automatic failover from a uptime perspective, that's great. That, you know, you don't have to wait for Chris to get a text and then log on and then say, I'm going to promote node C. So from an uptime perspective, it's great, but, you know, somebody still needs to potentially deal with the fact that there's you know, logs that have not been pushed out and potential loss of data. And if you have like financial information in this Oracle database, Steve, right? Like, oh, you can't just suddenly have, you know, $10,000 disappear.
Yep, agreed. Yep.
And I think this is one of the big things to kind of highlight is we're kind of lumping two things together here. One is the data replication aspect and saying, okay, I need to make sure that this data is copied over. And then the second one is the coordinator, which is deciding, should I do some kind of failover action or not? Okay, and you'll see this like, you know, you know, like Oracle, for instance, has multiple mechanisms for doing replication, but only one way. Last time I checked, I could be wrong. It's a couple of years out of date, but like only one way of doing that coordination, which only works with one of the replication models. So there's a lot of mix and match with the software out there, and it really comes down to being technology specific.
Yeah,
they follow patterns, but the details are definitely technology specific.
So I watched a Cloud Spanner video recently. So they talk about how do they do the write. So by the way, Spanner used a single leader replication scheme. So the write we send to the leader, and before leader commit the write on his own machine, it will send out some specific number to some replicas and get their acknowledgement. After that, it will commit the write. So this means if this leader fails, then there's no data loss there, because we know before the leader do commit the write, there's a number of replicas have their mutations. So yeah, that's how Spanner does it.
Yeah, so that's where you have synchronous forwarding of information, where basically the leader cannot acknowledge success until it is sure that N replicas have received.
Yeah, but not all the replicas, just a number. Yeah.
Right. Cool.
Thank you. There's the quorum section down further, which I think that's more a bit of that model. With regards to, it still needs a quorum of stuff to respond, not necessarily there's a quorum necessary for leadership handling. And that, again, it's the replication model versus the coordination model.
Yeah, one thing I find a little, I don't know if it's confusing or complicating, is that there are two layers here. I'm going to confess to some real weirdness. I have a NAS in my house, a network attached service, which runs RAID. So at the physical level, everything that's written to that NAS is replicated, and the NASs can replicate each other because one copy is always offline. But so I think to Stephen's point, like if you install Oracle on a real server, you're probably going to have some sort of RAID storage attached to it. So you'll get local replication. And then in some of the conversation, we're talking about transactional integrity. And if you think about like just your operating system, if you have multiple users on, you know, you get into the whole system of locks and synchronous integrity to make sure that your state stays known. So I think there's two pieces. I think there is a hardware piece, and then there's a software, which is specific to any solution you're going to come up with.
Yeah, thanks, Stephen. So I love this. So I appreciate people sharing, and you know, this book is talking about concepts, and it's also, you know, a couple years old. So you know, you get to specific products, and then you get to specific use cases, and you know, there's interaction of a lot of different components. So we haven't yet talked about transactions and things like that, but ultimately these are the issues, and so it's cool to be able to talk about these things. So if I can move on, I'm not going to go into tons of detail. I've got stuff in the notes, but basically there's if I remember right, there's 3 examples given of how replication lags. So even if you have single leader, you have no failure, everything's just running, you can still have phenomena that doesn't look right to the user. So the first is reading your own rights. And so it would be very weird if I went into my profile, I said, change my email address, click save, it said profile saved successfully. I then refresh my screen and I see my old email address. Okay, and so that's the problem that they're dealing with here, is because when I refresh my screen, I might be reading from a different replica that hasn't yet received. It will eventually, but at the time that I refresh my screen, it hasn't received that update of my email address from the leader yet. So that's a problem with read your own rights consistency. So then monotonic reads is the problem where things look like they go backwards in time. And so I think I might have mentioned this last week. You know, I'm looking at baseball scores and I see, oh, the Yankees, it looks really good. They just scored a run, so they're up 1-0, and they have the bases loaded with no outs. So I'm thinking to myself, well, that's a really good situation for the team trying to score. Maybe they're going to score again. So I refresh my screen, and then it says the score is 0-0. So I hit a replica that didn't even get that first run scored. And so instead of 1-0, it actually went back in time. It says 0-0. And then the other thing that you could see that's not really a problem with single leader, single partition, but you can get this situation where you have rights appearing in the reverse order. And so the example they gave was, you know, you get an answer before you actually see the question. So these are the kinds of problems that we can have, and this is even before you get into other more complex situations. So if you really want to make sure that to avoid these, the author mentions, we can do transactions, that's chapter 7. And then other ideas are going to be in chapter 9 and then ultimately in part 3 of the book. So that's the first part. That's just dealing with general replication issues and how single leaders implemented. Any other comments or questions before we move on to multi-leader? Okay. So ultimately, single leader is going to be easier. It's going to be easier for you to have, for example, like durability guarantees and things like that. But it is not going to scale as easily. And that's why we have multi-leader and leaderless. So if you have a single leader and you have multiple data centers and you have a global product, you know, let's say your Facebook, then saying that all rights have to be written to the San Francisco data center. And so even if you're in India, Australia, Europe, all of your rights have to go to that San Francisco data center. That's going to be problematic from a performance perspective. And so you could easily imagine that you would want a multi-leader situation. So maybe you have one leader in each data center. That's a pretty common configuration, pretty intuitive, right? Another example of the same technology is where you have offline operation. So actually my company uses this. So we use Couchbase. And so our clinicians who have tablets, if they don't have a cellular signal where they are, then essentially they act as a disconnected node, and therefore they become their own leader. And it uses multi-leader replication, where when you get connectivity again, then you sync with the other leaders. With the idea being that, you know, our corporate data center is the sort of, I don't know that there's an official term for it, but it's the primary, it's the main leader. And then another example they gave is collaborative editing. So Google Docs is essentially this giant multi-leader replication where people can be editing the same document at the same time. All right, so we have all the same read problems that we talked about with single leader replication, but now with multi-leader replication, in addition to that, we now have the possibility of write conflicts, because one person can say, update this particular key on leader A, and a different person can update the same key on leader B, and neither of the two leaders knows about it. And as they start trying to propagate that information to everybody else, then all of a sudden you've now got conflicting rights to the same thing. And the question is, what's supposed to happen? So a few comments here. So if it's possible to design your user level application to avoid this possibility, that's really the best, because write conflicts are not easy to resolve. And then a few things mentioned here. There's more later in the chapter. So you can say last write wins. So you have some sort of timestamp or arbitrary ID. You're potentially going to just lose data and not even know that you lost data because you get two writes and one of them wins. The client was told that other write was successful, but it's gone. A similar thing is, instead of just using some arbitrary thing like a timestamp, you can just simply say, well, whenever these two servers have a conflict, then I'm just going to number them, and I'm going to say this server has a higher number, and so this server always wins. Same problem with loss of data. You can merge the information, and so that would be a way where you don't lose information, and then theoretically, I guess you would hope that a user at some point would see, oh, we have these two conflicting things. Ultimately, if you don't want to keep this concatenated funny thing, then you pick. And so then the third write would basically say, okay, now this is what we want to keep. And then the other thing you can do is you can have a conflict log. And so I've seen, simple applications, a lot of them, they'll just have a conflict log. And so you just alert the user and you say, here's a problem. We've kept track of it, so we haven't lost anything, but you need to go look at it. And if you don't look at the conflict log, then things don't get resolved. And then the author mentions that if in your application you understand the dynamics, then you can say, well, in this situation, I know that we want to keep this. In that situation, I know we want to keep that. You can write your own conflict resolution logic And if you're going to do that, then there's two places where you could potentially be run. So one is on the right. So it's when you have two competing writes and that's detected, then you say, now let's do something. Let's try and resolve this right now. But the other possibility is that you don't do that. You wait until someone tries to read this. And at that point, when they detect that there's two alternate versions of things, then you either run the automated code to pick the winner, or you can then prompt the user and you could say, hey, what do you want to do about the fact that we have two competing writes here? The next thing that the author talks about are some of these automatic things. So I am not familiar with these. I don't know if anybody here has any experience with, but there are these conflict-free replicated data types, these CRDTs. I have not used those, but they have built-in sensible conflict resolution rules. There are these mergeable persistent data structures. I don't know if anybody knows what the difference between three-way merge functions and two-way merge functions. And then this operational transformation algorithm that's used by Google Docs and other applications. So if anybody can help shed some light on any of these three, this is not my area of expertise.
So the three-way merge versus a two-way merge. Usually a two-way merge is just this is what I want it to be, and this is what it currently is. So I'm looking at those two items, right? The three-way merge becomes this is what one thing thinks it is, this is what another thing thinks it is, and this is what I want it to be. And then you look at the diffs between all three to try to figure out which ones you want to win. So that's that on the mergeable, or on the two-way, three-way. The conflict-free is one of those. I've seen it done inside of some database schemas and layered on top of other things. So like you look at the, it's the, sets. It works well for sets. It works well for ordered lists and counters. I don't know about ordered lists. That one I keep getting, that one's hard to reason. But like if you can think of, instead of recording, this counter needs to be 12, and then it needs to be 4, and then it needs to be, 7, and whatever, you can say, well, add 12, subtract 8, add 3, and then addition, subtraction are communicative, so you can kind of resolve that without any real problem. That's kind of the idea behind the CRDTs.
I see. Or even simpler, if all you have is increment and decrement, because it's commutative, it doesn't matter whether client 1 said increment and client 2 said decrement. It doesn't matter which order. You can apply them both, no matter what.
Yeah.
Because you understand the rules of this is only counter, as opposed to as opposed to the standard logic would be, it used to be a 3 when I went increment and I say write 4. Yeah. And then the other user says this used to be a 3, write 2, and now you don't know what the heck people meant.
Yeah. Well, and it's also a space versus consistency trade-off. So if I'm recording the increments and decrements, I have to record them back however far I need to do it. So I may be recording like 100 values. Whereas if I just want to record my final counter value, I just record one integer, right? So you kind of run into those trade-offs.
Thanks, Chris. Anybody know how the Google Doc algorithm works? I could have looked it up, but I didn't have time.
I got asked on a basic data science interview on like whiteboarding question, how would you make Google Docs? Let's just say I wasn't prepared for that.
Oh man. Doesn't occur to me as data science. Occurs to me as something else.
Yeah, it was like, I think the third round of interviews, it was with just a couple straight software engineers, and that's what they wanted me to do, which yeah, I was ready for data science stuff, but not for that.
They work with the closest cluster which they can access. There is a, you know, I don't like very much the presentation of the book because they just pile up the number of problems without much of solution. I would, at this point, if I would know anything else, I would feel like my feet are off the ground, rather uncomfortable. Anyway, there is a, if you're like me, you can Google ACID versus base and add the word databases, one word. And you see that base is what basically available, soft, safe, and what eventually consistent. And I personally find the terminology touching. It has a promise, you know. Anyway, the thing is that they save everything on the closed cluster, which is closed to you. And you communicate only with this cluster. You don't see what happens on others. They just propagate their changes across other clusters while you're working. And eventually it is consistent.
Yeah, but I think the really tricky part, Maya, is what happens, what's the algorithm where if you and I open the same document and we both start typing characters in the same sentence at the same time, right?
Okay, I did it.
That's where this operational transformation algorithm has some logic to it.
Yes, I understand. And I did it, but I did it here, I mean, with a person who was in San Francisco. And it looks like we were just directed to the same cluster because, well, it looked like, you know, we were working at the same time.
Mm-hmm. Yeah.
I don't know what would happen if the person would be in, say, Australia. Didn't try it.
Yep. Yeah, obviously the farther and slower, the more it exacerbates the problems. But the problems can theoretically happen even if you're, you know, super close. They're just less frequent.
Oh, yeah.
All right.
Mm-hmm.
Anybody else? Any other comments or questions? All right, so moving on, the last section under multi-leader is just topologies. So common topologies, you can have all to R, all to all, so just a star where everybody talks to everybody. Well, actually, I shouldn't call it since it's a different star, but also you can have a circular, and the vanilla simple circular is just a unidirectional ring. You can have more complex multi-ring or whatever bidirectional rings, but the book that just starts with the simple building block, which is a unidirectional ring. And then a star type structure would be you have a central hub and everything is floating around it. You can generalize it to have more hubs. You can have a tree shape, but the whole idea with circular and star topologies is that data being forwarded now requires multiple hops. All to all, it's just a single hop from one to all other replicas. In a circular or star topology, any one individual node isn't responsible for talking to as many other ones, but instead what it requires is it requires multiple hops. So there's efficiency from sort of packaging up multiple writes and then sending them together on multiple hops. But then you basically need to keep track of which nodes have seen these writes. Otherwise you run into the possibility of an infinite loop where you're just forwarding the same write over and over again. In a circular star topology, you also have to worry about whether a node goes down. If in a star topology, if the central hub node goes down, then in a simple star, then nobody can talk to anybody anymore. So it's a single point of failure. And then the author mentions that the consistent prefix reads problem, you know, you can still have this problem with the all to all, And then at the very end, we're going to talk about version vectors, which, you know, Chris, you mentioned that these CRDTs, they're going to take up a little bit more space in order to trade off for these better properties. You know, version vectors can handle generically without having specific data structures with limited APIs on what interactions are allowed. And oh man, that seems to me like a lot of information that you're now going to be storing even for just like a single int. All right. Any questions about multi-leader before we get to leaderless? All right. So leaderless replication, basically you can either think of it as you have no leaders, or basically you think of it as every single node is a leader. And so Amazon Dynamo is really the product that sort of led the resurgence in these leaderless replication methodologies. And when you get down to the actual implementation, if you're needing to talk to multiple nodes, either the client can directly talk to multiple nodes, or in some of these applications, you actually have this coordinator that sits in between. And so the client only talks to the coordinator. It doesn't necessarily know that behind the scenes, there's X many different nodes that are being talked to at the same time. So the benefit of leaderless is that when you do an operation, instead of having a single point, you can go out and you can just simply say, I need a sufficient number of nodes to be up, and then the result will be considered successful. And so if you're trying to do a write and some of the nodes are down, no biggie. As long as you have enough of them, what eventually we're going to talk about, a quorum, then the operation can be successful. So when you're doing read operations, you also now need to read from multiple nodes in order to, and if you have a sufficiently large number of them, then some of them may have older, stale versions, but other ones will have the new versions. And basically, as the client, if you get back 2 responses and one says, well, the version 3 value of the counter was 4, but the version 4 value of the counter was 5, then you know, okay, I'm going to use the newest version. I'm going to use the version 4 value. So ultimately, the property that, if you do a little bit of math, that you come up with is, if you have n replicas, then the number of nodes required for a write, W, and the number of nodes required for a read must be bigger than that. And if you do that, if W plus R equals n plus 1, then basically you guarantee that for any number of nodes W that you wrote to, and any number of nodes R that you read from, that actually there must be an intersection. There must be at least one node that is in both of those. And so that's the fundamental business behind quorum. So an easy way you can do it is you can have an odd number. And so if you have 5 total nodes, then if you have the same number, that's just over half. If you have 3 reads, 3 writes, you can guarantee that anytime if you write to 3 nodes and somebody else reads from 3 nodes, that at least one of those nodes must be in common. And then basically, if you do 5 and 3, then basically you can tolerate 2 failures, and the system can still work. The more extra nodes you have, then theoretically the lower the latency, because you're only waiting for the first 3 to come back. So if you only have 3 nodes left, then you need every single one of those 3 to respond. If you have 5 nodes and you're waiting for 3 responses, then you can send asynchronously information to all 5. But as soon as the first 3 come back, then you can go in and you can acknowledge that this was a success. So getting into the weeds a little bit, there's problems that you can have. So obviously choosing numbers W and R that are less than or equal to n can cause problems because it doesn't have that quorum guarantee. But even with quorums, you can run into sloppy quorums. You have issues with concurrent writes, both of which we're going to talk about. But then you even have other edge cases. So if you do a write and the write fails, so we don't get a quorum, and the client knows, okay, I have no guarantee that this write actually succeeded because I didn't get a quorum. But the problem is that the nodes that did actually receive this write, they have no way of knowing that the operation failed. So they're not going to roll back, and they're going to have incorrectly a newer value than actually what was successfully written. Another place where you can get into problems is if you have a node that fails, when it comes back up, it needs to get caught up on everything. And so if it gets restored with a snapshot from node B, well, anything that's not the most recent value on B has now been copied onto A. And so you can kind of do the math pretty simply, and you can see that, oh, in fact, if you do a read from the wrong set of nodes that includes both A and B, you can think you've got a quorum, but in fact, because now these nodes are further behind than you expected. So quorums do have a guarantee when everything is up and running and working perfectly, but there are still edge cases to deal with in reality. So in terms of stale nodes, what can you do? With leader-based replication, you generally speaking have some kind of version number associated with things. And so you can easily at any point in time say, you can go to each node and you can say, what version of information are you aware of? And if, say, for example, the server's running really slow for some reason, or if the network connection is really slow, then you can actually see, holy cow, this server is on a much older version. Whereas typically, you know, the nodes are going to be on very similar versions of information. The problem with leaderless replication is that there's no sequence in which writes happen. And so therefore it is possible to have one particular key that's very up to date, but you can have another key that's really ancient. And just because nobody's looked at it, you don't even realize. So there isn't really a formal definition. There's no simple formula that says where you can just look at the state of your database and you can say how far behind is replication, how current is it, or how far behind is it. All right, sloppy quorums is this topic where if you have node failures and you don't have enough nodes for a write, the standard rule says you're supposed to just return an error message. But what you can do instead of returning an error, if you want more availability, is you can say, well, I have these other nodes that would normally be storing different information, but I'm going to temporarily store the key on here. And when some of my other nodes come back, then I'll use this hinted handoff. I don't know why it's called hinted handoff, but basically it'll then push it back to the nodes where the data is supposed to be on. And so that's a sloppy quorum. And so the idea is that this will give you some level of guarantee around persistency because you're spreading it out over W nodes. And so there's a heavy level of reliability, but then you're really increasing the chances for, you know, like stale reads because now again it's not a true quorum anymore. All right, let me pause here real quick. I know that we're kind of running out of time. Ryan, I don't know if there's anything in the chat, any questions or anything like that. I see a few chat messages. Any questions? Okay, so then just moving on to finish out this chapter, Multi-data center operation, there's a few notes that the author gives. So you don't necessarily want to treat all the nodes the same. So if you have like, you might want to implement it so that you guarantee that you have like some of the n nodes in each data center and they're all spread out. But also you can design architectures that specifically expect slow connections between data centers. And so maybe they mentioned like React uses the initial replication within a data center, and then it uses a multi-leader strategy to do sort of eventual consistency, spreading things between data centers. So then the last big topic is this concurrent rights business. And so this is how to deal with, you've got multiple rights, and if two people are trying to write to the same key, how do you resolve these things? And so there's a little bit, talks about what is concurrency. And so if A is aware of B, then B happened first. So if I know that B inserted something and I'm now updating it, then clearly that insert happened before I update it. But if two people are doing updates, two people are changing, the topic on a particular item, they could be doing it. And so regardless of wall clock time, they're considered concurrent if there's no causal sort of dependency between the two. And there's an algorithm here that they show where basically you track versions, and clients have to basically do a read before they do a write. And so then they can say, based on that read, I knew about version number X, and now I'm doing a write. And so then the server can maintain based on what writers knew about, what version they read from before they did their write, keep track of things, and they have to keep track of multiple values in the case where you have concurrent writes. And then ultimately, this can be extended to this version vector business where it's not just a single server, but you have a version number tracking per replica. And the main complexity whenever you do this is that if you do a read and you get back all these different versions, then when you want to do a write, you have to decide, how am I going to merge, resolve all the different information from the different versions that I read. And so I thought there was an interesting example in the book where a union operation was performed on a shopping cart. That seemed like a pretty safe vanilla thing. So if you have two different inserts and they collide, then you just put them both in. But that didn't handle the use case where somebody removed something from a shopping cart. So you remove it from a shopping cart, you refresh the screen, and now all of a sudden the thing that you removed is back. You remove it again, you refresh the screen, all of a sudden the thing that you removed comes back to your shopping cart. So, so that's the last topic, just to kind of wrap up things here for the replication chapter. So any questions, any last comments?
I don't have a question, but I have a suggestion. Maybe somebody can do these experiments with Google Docs. And well, if they're sufficiently far enough from each other, like there are definitely different Google data centers which handles the information.
Yeah, I mean, I think, even if we're close, I mean, if you are in the same document, we both put our cursors at the same spot, we both start typing like mad, right? Mm-hmm. It's kind of interesting to see, like, is it going to do something where it keeps all of the characters you typed and all the characters I typed together, right? Or at any point, are you going to see them interleaved? So I don't know. I'm not really sure, how it does that. But you can imagine that most of the time, you're not going to run into really bad collisions like that. But yes, there are going to be edge cases, right? So I can do things like I can delete 10 pages in one fell swoop.
But Google keeps the versions other people introduced. And unless you delete them, they're here.
Yeah, but I'm just saying that I don't even know. I don't know what the algorithm is. I don't know what is, if we have 5 people that simultaneously all try to do inserts into this one paragraph, and at the same time I delete the entire paragraph, what is the final state? Is the final state no paragraph? Is it the original text is gone but the 5 inserts appear? Like they're I'm sure you know, we can look up on the internet what that algorithm is. I just don't know off the top of my head. But in the book, what it's saying is that specifically the algorithm is dependent on the fact that it is a sequence. So in this case, a sequence of characters. There is something fundamental to the algorithm that it works on a sequence.
Yeah, I
ordered
understand.
list, basically.
But if somebody can do an experiment, I will be very curious.
Okay.
I think one of the things that was interesting to me is how reliant we are actually on high expectations of the networking, that we're going to have somewhat low latency and have enough throughput to handle the possibility of a failure in the transfer and all of that stuff. I can imagine that in certain cases you might end up significantly backed up, and that might be significant network traffic. So it's just kind of interesting to think about how good our technology actually is in that regard.
Yeah, that's a good point, Ryan. I mean, you don't expect your Facebook or your Twitter feed to be, you know, incomplete, right? You just expect it to be perfect. Yeah, so definitely there's going to be follow-on in the chapter 7 on transactions. There's going to be follow-on in the chapter on consensus. So there are going to be ways to ensure certain properties for certain use cases. So for example, you know, banking, I'm sure, you know, they're not just gonna be like, oh, well, we had a stale read, we had a missed write, you know. And those are lower volume transactions, so they can probably, you know, tolerate the extra overhead. But, you know, the extreme cases, you know, your Twitter or something like that. And so you just need to be fast. All right, anything else from anyone before we switch gears and move on to the project and Kaggle discussion? All right, well, thanks everyone. I hope to see you next week on the NFL competition recap, and then chapter 6, the partitioning and sharding conversation.
Thanks for the recap, Ted.
Yeah, you're welcome.
Yeah, thanks, Ted.
Thanks.
Thanks, Ted.